Yeah, so thank you for the introduction, and thank you the IEEE Sensors for inviting me to talk on this paper that we published last year. So I'll go through a little bit of background on atom-based RF sensing and how this works. So effectively, we have a hydrogen-like atom, so a group 1 alkali metal. In this case, we're using rubidium. And what we do is we build a set of states where we optically pump the outer electron in the rubidium to a high-line Rydberg state using a 2-photon transition. The first excitation is done using a 780 nanometer probe laser. This pumps our electron from the ground state to the first excited state. We then counterpropagate this beam with our coupling laser, which moves our electron from the first excited state to the to a high-line Rydberg state. This high-line Rydberg state can be sensitive to applied RF fields. And what we actually see is a depopulation of the ground state. So our probe laser is then not absorbed. To be able to actually see RF detection, what we actually do is couple the Rydberg state with an adjacent state. This creates an upper and lower bound population and takes the coupling transition off resonance. So electrons which are still within the first excited state then decay back down into the ground state. And this breaks down the electromagnetically induced transparency, and we see the absorption within the probe. This is also similar to AC Stark effects as well, and is known as Altler-Townsend splitting within the states. So we're interested in sort of what the sensitivity limit of this and whether it can be a replacement for a traditional dipole antenna. To do this, we start by considering our system as a 2-state system. So we're interested in the dipole moment between our 2 Rydberg states. And this is given by the symbol just here. This is the electric dipole moment, which can be thought of as a charge separation. This is then multiplied by the measurement time and the number of independent measurements that we take. If we take the assertion that our measurement time is less than the relaxation time within the atom, which is approximately 6 megahertz, we can then actually rewrite this equation in terms of number of interacting atoms by using the relationship just below. What we find then is that our minimum field strength is equal to this equation here, where we've now introduced the integration time. So this is how long it takes us to integrate the signal and the relaxation time of the atom. This is great for low-speed communications, so very slow on-off keying. But if we want to drive our system faster towards the limit of the spontaneous decay in the atom, we actually have to make a slight adjustment to these equations. To do this, we consider the system where the integration time is equal to the measurement time, and the measurement time is approximately equal to the relaxation time. So what we find is the middle equation, and RS in this is actually just 1 over the relaxation time. From this, we're able to calculate out a traditional power density. But to do this, we need to consider that our atoms are effectively in a very small dipole antenna. So we have to calculate the the absorption cross-section for all of the atoms involved within the interaction. And when we do that, we actually find that our minimum power density is given by the equation here. And with this, we're then able to calculate out a graph which shows the symbol rate versus the noise floor. So the dotted line here is the conventional dipole antenna noise floor for thermal noise. And you can see when we're driving our atomic system towards the limit of spontaneous decay, there's a crossover region where a traditional dipole antenna would actually outperform a Rydberg receiver. But if we consider slower simpling rates, then we're able to actually potentially reduce our noise floor quite significantly. So with this in mind, we were then interested in looking at how our assembling rate, what the crossover region and symbol rate versus the two systems. So we could define where our ideal optimized position would be with regards to our carrier frequency. To do this, we rearranged the equations, and we actually found that as we go to higher RF frequencies, we can increase our symboling rate. This does have a limit threshold within rubidium of about 5 megahertz. But if you're in this frequency range, if you keep your symboling rate below that threshold, you'll be below the thermal noise rule. So we then wanted to test this experimentally. So we actually published a paper in the Journal of Applied Physics, and I'll go through some of the results that we saw in that experimental proof. So this is a simplified version of our experimental setup. Figure A actually shows our coupling locking system. So we actually use the electromagnetically induced transparency to lock our coupling laser to the specific transition. Figure B is then our RF detection. So although they're connected by a very short line here, they're actually optically connected through polarization maintaining fiber and separated by most of the space in the lab, so that we don't get interference and break down our locking signal when we're using the electromagnetically induced transparency. We have two beams passing through both vapor cells in the 780 nanometer regime. This is so we have a reference absorption signal when we're using our differential photodiode. So once we built our optical experiment, we wanted to compare this to a conventional all-electrical system. And in doing that, we also wanted to take power density measurements across the system. Because we were interested in doing digital modulation, we decided to introduce an intermediate frequency onto our carrier wave. So we actually modulated our intermediate frequency rather than directly modulating the 3.5 gigahertz carrier, which is what you can see here. So we did measurements at different points within our experimental setup. So in A, this is just our intermediate frequency generation and adding the encoding onto this. Figure B is then mixing that signal with our 3.5 gigahertz carrier, which is why we've got all of the additional sidebands, because we weren't suppressing those within this experiment. But the key results here to take away are actually in figure C and figure D. So figure D is actually our all electrical equivalency circuit, and figure C is our signal recovery from our all optical system. And what we can see is there's a significant increase in the noise of our Rydberg receiver. The reason for this is we were actually modulating the current of our laser, which was introducing additional errors into our system. We've since gone away, fixed that issue. But for the purposes of this paper, it was an interesting discussion point. But you can see similar features between the two figures for the all electrical and the Rydberg receiver itself. So once we had that system up and running, one of the other things we wanted to do was sort of actually demonstrate a communication system. So we chose 3 different types of encoding systems. So we used phase key shifting, quadra-phase key shifting, and 16 QAM on our intermediate frequency. We were able to reconstruct our symbol rates and measure the errors that were induced. And you can see as we approached on the bit rate the intermediate frequency limit, our errors increased exponentially. These are currently intrinsic results. We haven't actually done the analysis as of yet to be able to compare the different encoding types, but this is actually on our list of things to do. So sort of some rough concluding marks. We presented a theoretical analysis of where we think a Rydberg receiver would potentially outperform a conventional dipole antenna. We demonstrated digital communications on that receiver and without the need of a local oscillator, which is generally what's done to most other labs that are looking at this, they have their signal field and their oscillating field. They mix those two in free space and down convert, whereas we did this using an intermediate frequency directly encoded onto our carrier frequency. We've also managed to actually passively down convert our RF encoded signal onto an optical signal and read that out directly from the photodiode, which could have potential power saving benefits when you consider this could easily be distributed into a fiber optic network. There are some key advantages, but the technology itself is still in the very early stages of its research at the moment. So some of the future work that I have outlined within my PhD and with BT, the company I work for, is actually looking at different higher order modulation schemes. So we've recently tested 126 QAM with some success. But we're also looking at introducing frequency division multiplexing by targeting two adjacent Rydberg transitions, which could allow us to increase the overall data rate while not losing signal quality. As I said, we have actually improved our locking signal, which was the biggest cause of errors within our system. So we can now actually modulate our system up at 5 megahertz, which is approximately the spontaneous decay rate. And we want to sort of explore the limits of the sensitivity versus encoding data transmission. We also want to demonstrate an LTE uplink using the IoT standards in 5G communications. And finally, we want to scale this down from our bulk optics experiment into a fully fiber integrated system. This work's actually been sponsored by the Royal Commission, the Exhibition of 1851, who are currently sponsoring my PhD. And I actually sit and work at the University of Birmingham in the UK's quantum timing and sensing. So if you're interested in more details on any of this, I have 3 papers which go through in more detail than I had time here for. But any questions?